Hello, today we're going to continue with section 7.7, but now we're going to talk about power functions. And so we've really, throughout this whole chapter, we've taken a lot of advantage of the linear property of the Laplace transform and being able to break up sums into, and taking the Laplace transform of each term separately. And so now we're going to take that to the extreme. We're going to consider an example. F of t is going to equal sine t over t for t not equal to 0 and 1 if t equals 0. Okay, so that's our function. So now this is a continuous function, even though we have defined it separately, because it is continuous. Of course, it's continuous wherever t isn't equal to 0, because it's just a continuous sine function divided by t. So as long as we only get into trouble where the denominator equals 0. But it is, in fact, continuous because if you think about the limit as t goes to 0 of sine t over t, you can do L'Hopital's rule on this, and this actually equals 1. So even though you can't plug in, sine of 0 over 0, it's still approaching 1, and so this makes sense as a continuous function. And in fact, by magic, I can get the plot of this function from Wolfram alpha. Now, we don't have the tools we need to take the Laplace transform of this directly, but we can rewrite it. And what we've always been doing in most of our examples is we've been trying to rewrite our functions as sort of powers of t, and that has helped us out be able to take Laplace transforms of these rational functions. So let's think about the fact that sine, do it in black, sine of t, we can write the Taylor series out, and it equals t minus t cubed over 3 factorial plus t to the 5th over 5 factorial, etc., minus t to the 7th over 7 factorial, etc., etc. And so that means that we can divide by t, and so then we take, let's see, f of t equals sine t over t, and then that's going to equal 1 minus t squared over 3 factorial plus t to the 4th over 5 factorial, etc. t6 over. And of course, this is true. This expression as a power series holds even for t equals 0, because if you plug in t equals 0, you just get 1. So that's another way that you can tell that this is going to be a continuous function and that everything is going to match up. So now it's not necessarily obvious that if we take the Laplace transform, that we can take the Laplace transform of an infinite sum, because our linearity only tells us that we can break up finite sums. And it, in fact, takes a little bit more advanced math to prove that the Laplace transform is going to hold, but it does, and we'll just accept this now. And so that means that we're going to take the Laplace transform of f of t and do this term by term. So we get the Laplace transform of 1 minus 1 over 3 factorial Laplace transform of t squared, etc., etc. There we go. And these are all things that we can look up. And in fact, the powers of t we have a nice formula for. So for 1, we get 1 over s. And then for t to the n, so let's see, we actually get minus 1 over 3 factorial times, so Laplace transform of t to the n is n factorial, so in this case it's 2 over s, and then one more power of, so n plus 1. So in this case, that would be 3, and so forth. So we'll get, for this next term, we would end up getting 4 factorial over 5 factorial s to the 5th, and so forth. 6 factorial over 7 factorial s to the 7th. And we can simplify this a little bit. Well, really a lot, actually. So we've got 1 over s. And then the 2 factorial over 3 factorial is just going to leave a 3 on the bottom. So 3s cubed plus 1 over 5s to the 5th minus, 1 over 7s to the 7th. And I forgot my ... on all of those. And actually, as it happens, this is the formula for arctan of 1 over s. Okay, so this was a pretty useful tool for calculating the Laplace transform of a function that we otherwise wouldn't have the tools to do. So now we were able to do this because we had integer powers of t in our function. But one thing that we haven't seen yet is how we can deal with powers that are non-integer functions, like t to the 1/2, like a square root function. And so in order to talk about those, we need to define a weird new function. So I'm going to define this definition. And this is called the gamma function. And it's called a gamma function, I guess, because it's notated with a capital gamma, Greek letter gamma, which kind of looks like a hangman's, thingy, whatever that thing is called. So gamma of r is defined by this integral. Integral from 0 to infinity e to the negative u times u of r minus 1 du. So u is the integrating term there, and that's defined for any positive r. So what's nice about this is like a generalization of the factorial function. And the way that we see that is that it has this nice recursive relationship. So let's think about, let's go to black again, I guess. And let's think about gamma of some number r plus 1. Because the nice thing about factorial is that if you have, you can define factorial by saying, it's all the integers multiplied together, all the integers from 1 to n. But if you want to know what n plus 1 factorial is, it's just n plus 1 times n factorial, right? So same thing here, we care about what is happening to gamma of r plus 1. So we'll just write out the definition. Integral from 0 to infinity e to the negative u to the r du. Now we can write this as a limit as capital N goes to infinity, 0 to n, same thing, u to the r du. Now this thing we can do integration by parts, because we want to relate this integral back to something that has to do with gamma of r. So we want an integral that has a u to the r minus 1 in it. So that gives us a clue about how to do integration by parts. So let's do integration by parts. And we'll set, U is not going to be a good term. So let's do V equal, okay, so if I'm going to have to not use U, I'm going to write this out. So let's use V and W instead. So the integral of V dW equals VW minus the integral of W dV. Okay, changing the letters up is really kind of making my brain hurt. All right, so if we want to have we basically want to get the integral of this u to the r, or the derivative of that into our new integral, because we want to go down a power. So that is we want that to be our dv. So u to the r will be our v, and then dw is e to the negative u du. dv equals r u to the r minus 1 du, and w equals negative e to the negative u. Okay, that's easy enough once we got everything sort of sorted out. So now we can write this as the limit as n goes to infinity. VW, so negative e to the negative u, u to the r, evaluated from u equals 0 to u equals n, minus the integral of w dv. So the minus and the w is going to give us a plus. We get the integral from 0 to n of w dv, so that's e to the negative u times r u to the r minus 1 du. Okay, so plugging things in, we get limit as n goes to infinity, negative e to the negative n times n to the r. And then when we plug in u equals 0, that goes away, so we get a minus 0. And now I'm going to write I can pull this r out to the front, and I'm going to do my limit again just so that I can think about each part separately. 0 to n, e to the negative u to the r minus 1 du. Okay, so now this part, this last integral and the limit is, if I change the limit, or if I put the limit in, and that is the integral from 0 to infinity, so this is exactly equal to gamma of r. And then this limit here, as n goes to infinity, we get e to the negative infinity, and so that goes to 0. And so then we get exactly what we wanted. We get r times gamma of r. Okay, now let's go back to what I said before about how this relates to the regular factorial function. So before we disappear the top part, let's write this relationship again. Oops. Gamma of r plus 1 equals r times gamma of r, okay? So there we go, we've got this nice property. So what about if we have, let's think about what this means for some particular numbers, like natural numbers. So first of all, gamma of 1, we can write out the definition. So this is the integral from 0 to infinity of e to the negative u, u to the r minus 1, which in this case is just going to be 0 du. Of course, that is just 1. And then this whole thing is going to equal 1. And how I know that is because I went to Wolfram alpha. And there we go. Proof. I mean, of course, this is a pretty straightforward integral to do, even with the infinity, but I'm not going to do the details here because I know that you all know how to use Wolfram alpha. So now what about gamma of 2? Well, now I can use the green result. So that's going to equal, with r equals 2, we get 2 times, r would equal 1. So we get 1 times gamma of 1 equals 1. Gamma of 3, now r equals 2, so we get 2 times gamma of 2, which equals 2, etc. 3 times gamma of 3 equals 6. And we're just going to do this out probably just this one time. 4 times gamma of 4 equals 24. And so, I mean, you can see this. This equals 1. This equals 1 times 2. This equals 1 times 2 times 3. 1 times 2 times 3 times 4, etc., etc. So this, when you're plugging in natural numbers, this is just the factorial function, which is exactly what we wanted. So yada, 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 gamma of n plus 1 equals n factorial. So this is what I mean when I say that this is a generalization, that the gamma function is a generalization of the factorial function, because it is exactly the same as the factorial function for natural numbers, but then you can also, it has a similar property and is defined for any other number. So now the last thing we're going to do is, the whole point of introducing this function is that we're interested in figuring out a formula for the Laplace transform of t to the r, where r is not necessarily an integer or a natural number. So let's, oops, it shouldn't be an n, that should be an s. It's a function of s. Okay, so let's write out the definition. E to the negative st, t to the r dt. So now I'm going to do a u substitution. I'm going to let u equal st, and then du equals, remember we're doing integrals with respect to t, so the du is going to be s dt. Okay, so let's plug this in. We get the integral. The limits are going to stay the same because when t equals 0, u also equals 0, and same with infinity. So we have the same limits. E to the negative u. T equals u over s, so we have u over s to the r. And then dt is du over s, so we have 1 over s times du. Now we can pull out all of those 1 over s's. So we have 1 over s to the r plus 1, integral from 0 to infinity, e to the negative u, u to the r du. So now this is looking kind of familiar. Let's pull in our definition of the gamma function from before. Ta-da! This is not exactly quite the same because over in the blue we've got r minus 1, but we can think about this. Instead, we can write this as, we've got 1 over s to the r plus 1, and then this is going to be gamma of r plus 1. So putting this all together, we've got a nice property for the Laplace function. The Laplace function of t to the r is equal to gamma of r plus 1 over s to the r plus 1. And note that if n is, let's see, if n equals 1, 2, 3, etc., then LT to the n equals gamma of r plus 1 equals n factorial, like just we had up before. So n factorial over s to the n plus 1, which is the same familiar formula. So this is, again, just a generalization, but now it applies for any r greater than 0. Okay, and so there we go. That's it. Thanks.